production thing. I'm here today to talk about multi-laser laser powder bed systems. I'm excited to talk about these powder bed systems and the effect of multi-laser processing on part quality. So in case you aren't familiar with Velo3D, we're, like Yuping said, a fairly new entrant into laser powder bed fusion systems. We were founded 5 years ago with the intent of extending the process. So our goal was basically to be able to print parts that are considered to be impossible to print on today's laser powder bed systems. And really, kind of at its most basic level, what that means is reducing the amount of supports that are required to successfully print a part. So in conventional laser powder bed systems, generally any downward-facing surface that's 45 degrees or below will require supports to successfully complete. And our main focus, at least originally, was around pushing that as low as possible. So we've been able to push that down to 10 degrees and in some cases 5 degrees of material geometry without supports. We started to develop the process, and one of the things that we ran into pretty quickly was that the existing equipment and the existing software weren't really capable of enabling the process that we've developed. So when I joined the company 3 years ago, it was kind of my imperative to define a software and a system that would allow us to print, to actually execute this process, where the process window is much tighter than it is with a more conventional LF system. So that's Velo3D in a nutshell. And I think really our goal is to help not only expand the application space by allowing people to print parts that you can't run on other systems, but to also to focus on pushing Metal AM further and further into production, serial production, because that seems to be a common goal that I hope we all share. And in many cases, production means melting metal faster. And I think that one of the big things that we have to focus on as we move more and more into production is reducing part cost. And the best way to reduce part cost, because most of the part cost is associated with machine amortization, the way to reduce part cost is really to melt metal faster. And it's honestly that simple in most cases. There are a couple of ways that you can approach melting metal faster. One approach that you might take is if you have a 400 watt single laser system, put an 8 kilowatt laser on it. In that sense, you would absolutely melt metal faster. It would probably not give you the outcomes that you want. The material probably isn't quite what you're looking for. The resolution wouldn't be great. So maybe it's not the best solution. The other solution is to add more lasers. And if you add more lasers, you can melt metal faster and still do so within some of the limits of physics when it comes to actually melting metal and making good material at the end of the day. So more lasers means melting faster. That's the goal of the serial production. More lasers is not necessarily an easy thing to implement. And I think that there's a lot of complications, and some of them are very subtle when it comes to multi-laser systems. So I've outlined four issues that you might run across when working with multi-laser systems in a laser powder bed setting. The first one is laser alignment. And this is, I think, particularly relevant, especially at aerodev, because aerospace parts tend to be big a lot of times. So you're trying to print a part that essentially fills up the build volume. So as an example, this part on the right, which is a proxy for like an exhaust manifold, is a part, if you saw it at our booth, it's about a 300 millimeter diameter. It's 300 millimeters tall. It's a pretty massive piece of ink. And this is the kind of part that you run across in aerospace, as opposed to medical, right? In medical orthopedics, you are printing thousands of small parts in a lot of cases. If you're doing hip cups or spinal implants, you can print very small parts, and in that case, laser alignment isn't as critical. And the reason it's not as critical is that you're able to assign one laser to each part. In the case of big parts, if you want to really capitalize on the throughput increase of adding multiple lasers, you're going to have to build one part with multiple lasers at some point. So laser alignment becomes very critical there. Thermal loads are kind of a subtle aspect of multi-laser systems. So it's not as simple as taking a single laser system and tacking on 3 more lasers and hoping everything goes well, because there's a lot that comes with adding more lasers that is pretty subtle. A lot of times the thermal management of the machine is not adequate to really take on that extra power. And if you're not maintaining your thermal conditions in the chamber appropriately, then kind of all bets are off on what you're actually building. So there are some architectural considerations that have to go into designing multi-laser systems that are really important for part outcomes. Soot removal, so I think it's pretty widely recognized that gas flow is a critical aspect of building good parts in laser powder bed systems. Soot removal when you're melting 4 times as much material is equally critical. You can generate quite a bit more soot, and you have to deal with that. So that can be in the filtration system, the gas flow, the inlet and outlet design, but also in the laser scheduling. And that's a big part of what you have to consider when you're looking at multi-laser systems, how to effectively schedule lasers to optimize throughput while still making good material at the end of the day. So just to go into a little bit more detail on each one of these, we're going to start with laser-to-laser alignment. And at its most basic, laser-to-laser alignment is when you tell the machine to point a laser at a certain point, making sure that multiple lasers actually point at the same location in X, Y. So that's one aspect of it, and it can be challenging. So each scan head has 2 galvanometers in it, and you have to make sure that the galvanometers are mapped correctly so that each scan head actually makes sure that the lasers are pointed at the same location. It has to be pretty accurate here. The other thing is that the focuses have to match, right? So you can't have different spot sizes from different lasers at different locations over the plate. Your focal planes have to be parallel, and they have to be on top of each other, and your laser-laser alignment has to be pretty spot on. So what happens if it's not? This is an example of a stacked cube print that we like to do to validate overlay. Essentially what we're doing is building a block with one laser, and then after a certain Z height, build a block with a second laser, and then go back to the first laser, and you can do this throughout the entire Z height and characterize at least somewhat quantitatively overlay mismatches. In this particular case, what we did was turn off the thermal control of the system. So we're not running an intercooler, we're not maintaining gas flow temperatures, we're just letting it run. And what you see is there's a shift in the second laser. One of the things that's interesting about this is if you look closely, the shift is only on one side. On the other side, it's pretty subtle. It's pretty well aligned. And this is actually something that we see that's indicative of chamber expansion. So if your focusing optics are moving away from your build plane, your point where the 2 lasers intersect moves. And your build plane is kind of moving through your focus. And what that does is it induces a shift in one axis, but not in the other. In the other axis, both of your lasers are pointed at the same point, and whenever your build plane moves, all it does is change the dimension of your part. So you'll lose dimensionality in one axis, but you'll lose overlay in the other axis. The other important question to answer here is, what overlay is good enough, right? How closely do my lasers have to be matched before there is no effect on the process, before the material is considered good? So we like to do a number of different tests, and one of them that I think is really illustrated is overlay-induced contour breakdown. So in this test, we're printing these inverted cones with different downward-facing angles, and we're printing the core with one laser and the contour with our other laser. So a dual laser system. And by forcing this specific offset in the overlays, you can see when the contours start to see these punch throughs and defects on different parts that indicate that the overlay is no longer good. And in this case, what you kind of see is with a 50 micron offset in either direction, the contours remain stable. The process remains relatively stable. If you get more than that, it starts to break down. You start to get surface roughness, some contour defects that aren't acceptable. And we have a number of other tests. We've kind of established that a 50 micron offset in overlays is generally good enough in terms of porosity, in terms of mechanical properties, in terms of the surface roughness. So 50 microns is kind of the spec that we set as an acceptable limit. That doesn't mean that you shouldn't try to do better, but 50 microns is a good place to be. So with the kind of the definition of laser alignment and the requirement that we're trying to hit, I want to kind of go through a thought experiment about printing a part with a multi-laser system. And we're going to print the most boring part possible. We're going to print a part that you should never, ever print on a laser powder bed system, which is a massive ingot canal. So our system is a 315 millimeter diameter build plate. It's a round build plate. And here, in a lot of the figures that I'm showing, we've taken a 250 millimeter diameter cylinder that's full Z height, so 400 millimeters tall, 8,000 layers of printing, something like a week of printing. And just look at how the laser-to-laser assignment and scheduling actually kind of works in the real world. So one of the issues that you can run into with large parts is alignment stability. I think the previous presentation highlighted that this is something that you should actually care about. It can change. And particularly, it can change because your galvos, the encoders, can drift, essentially. You can have them drift apart. You can have thermal changes in the system itself. And all of these lead to alignment shifts, basically. So just as kind of a thought experiment, if you have a build chamber that's 500 millimeters tall, right? And your focusing optics are somewhere up here 500 millimeters away from your build plane. If the material that the chamber is made of is stainless steel, you're working with a 16 ppm coefficient of thermal expansion, and your build temperature, the chamber temperature changes by 15 degrees C, your lasers will offset from each other by 40 microns. So you've basically blown your spec already with your 15 degrees C change. And while 15 degrees sounds like a reasonable amount of change, maybe too much change to have occur during the process, another thing to keep in mind is that when you're doing calibration for the systems, when you're doing alignment calibration, in general, most systems do this cold. You do this by putting a plate into a machine, burning marks on the plate, pulling the plate out and measuring it. And then when you go to run a part, you're going to be running for 7 days, right? So in that time, your thermostatic system changes. It can change quite a bit, enough to make sure that your alignment is no longer valid. So just as an example, this is indicative of a way that some machine manufacturers like to do overlay and laser assignment. So essentially, you take a part, it is a two laser system, you split it in half, you do core and contour with one laser on the top, so that's blue. You do core and contour with one laser on the bottom, and you just kind of butt them up to each other. So it's kind of like you're printing two parts very close to each other that end up being one part. If you're on a quad laser system, often you'll split this into 4, and you'll end up with 4 quadrants of a part that are printed in essentially the same way. This is well and good if your laser is aligned on layer 1, but when you get to layer 8,000, things move. And you can see this a lot of times in the overlay because the overlay will shift as a function of Z. So you'll actually start to see more overlay shift as you get higher in the part. And the question then is the part good? You didn't have a pause in the build. You didn't violate some of the build restrictions that you might have around building a part production. But the question remains, what's inside the part, right? Do I have an area in the part where I haven't fused the metal? On this overlay, is that okay for a dynamic mechanical test for high cycle and low cycle fatigue? It can be questionable at that point. So it'd be really nice if you could measure the overlay with the machine itself. The machine could basically take a measurement of its own optical health and provide you a report. So one of the things that Bell is really focused on is in situ metrology, making sure that the system can monitor its own health and provide that feedback to the user. This is an example, this is an actual screenshot from our machine user interface. And this is a pre-built laser alignment. So we can map the distortion of each galvo independently and then map those to each other. Report back your calibration values in X and Y for both lasers and provide this as a report. This is great, except it doesn't actually address the problem that I stated, which is you drift over time, right? So if you're going to build an 8,000 layer build, the really nice thing would be if you could do this in situ. So we did. We developed a way to do in situ laser alignment measurements, and you can do this arbitrarily. It's configurable at any layer or any sequence of layers. So we like to do this every 50 layers, 50 to 100 layers. And what we're doing here, this is a plot of a build where, again, we don't have our thermal management system on. So when you first start the build, it'll heat up, your alignment will shift, and that's what you see going on here. We turn on our automatic overlay correction, which basically is taking these measurements in this case, I think it's every layer. It's kind of overkill, but it's a concept of feasibility study. So you turn this on, and the system starts to actively control its laser alignment in real time to make sure that on every layer throughout the entire build, your alignment is correct. What does that give you? It gives you a part with no discernible overlay. So you can actually build parts that look like they were printed with one laser. You're printing them with multiple lasers. And as long as you have this active control turned on, you more or less cannot see the overlay between the lasers. So it's a really effective tool, especially when you're building big parts. So in addition to alignment, one of the other things that I mentioned was soot removal and laser scheduling. And those really come down to a throughput optimization. So one of the things you don't want to do is put two lasers on a system and then run one 100% of the time and the other one 50% of the time. You're not maximizing your throughput if you're doing that. You're wasting a lot of infrastructure and expense to not realize the full throughput gains that you could. And when you're looking for throughput optimization, one of the things that you have to consider, there's kind of two parts of this. There's laser assignment, how you break up a part to be assigned to the two lasers, and then scheduling. And so another way that we've seen people approach the laser assignment, which is also kind of an interesting way to get past some of the limitations of the previous scheme, is to run if you're on a dual laser system, to run core split up between the two lasers, but to then run your contours with a single laser. And this is interesting because you actually don't break up the contours, right? So you don't have this overlay mismatch where the contours are broken up. And it's kind of a clever way to get around this. There's one issue that you need to be aware of, though, which is it doesn't solve the problem again. If your core shifts, if one of your lasers is moving relative to the other one, what this does is it can mask the overlay mismatch that you see when your contours are donated up together. And as a result, what you really end up with is a subcontour porosity, which can be a sharp, jagged porosity, which is a real killer when it comes to high cycle and low cycle fatigue. So just because the part looks good on the outside with a single contour scheme doesn't mean the part is necessarily good. Doesn't mean it's necessarily bad, but it's something to keep in mind when you're looking at different ways to approach multi-laser assignment. So at Velo, we chose kind of a combination of the two that produces the worst possible result if your alignment's not there. And what we've done here is split the part into two. So this is our 250 millimeter cylinder. We split the part into two, and if you can see it, you actually have green contour coming down around the blue core. So not only are we printing the core with two different lasers, we're actually offsetting it onto the core of the other laser. So that if you have a laser alignment mismatch, it's brutally obvious. There's no way to hide it, which is a good thing, really, because if the system's not performing nominally and you're trying to produce aerospace grade parts, you should know if something's not right? So this is one method that we've come up with to kind of get us to this point. And then the other thing we do is move the interface around. So you're always moving the interface around. The reason we do that is because it makes a stronger part. So when you're building a brick wall, you don't line all your mortar up in one joint and hope for the best. You interlace your layers and build a stronger part. The other thing is laser scheduling. So soot is particularly bad if you're shooting through it. Don't shoot the smoke. This should be a mantra for all multi-laser systems. If you shoot a laser through the smoke, you get occlusion, you don't deliver the laser power that you intend to the surface, you don't fully melt, you end up with defects. So a really important thing here is also to schedule the lasers appropriately. And the way we approach this is also a little bit different. We choose a swim lane methodology. So this is a plot of the laser print order. You can see up here, this is our flow print preparation software. And one laser is starting here in the red, and the other laser is starting here in the red. And then as you progress through the layer, you're basically working upstream on each of these lanes until you get to the end, and then it's switching to the next lane. So in this way, you can make sure that your lasers are never downstream of the other laser. You're never shooting through the smoke. You can also modulate where this separation is occurring, such that you maximize throughput. So this is just the method that we've chosen to be able to optimize throughput while also not shooting the smoke. And again, this shifts around over layers so that you're kind of building your brick wall. So just as a story, when I joined Velo 3 years ago, I was the only person to join Velo who worked at Velo who had any additive experience. Everybody else was from the semiconductor industry, so they worked at Applied Materials, CALIBRATE, and Lamb, and our co-founder, Arel Milstein, asked me what our spec should be for laser overlay. And I said, well, you know, in my experience working with previous equipment, something on the order of 50 to 100 microns, I think would be an appropriate laser overlay. And he started laughing out loud at me. He said, you have to be kidding. 50 micron is your spec for laser overlay? And I said, yeah, I mean, at that point, I don't think that you could notice a difference. And he said, wow, at 50 microns, that would be a gross failure of the semiconductor equipment. There's no way that you could produce semiconductor parts with a 50 micron overlay, anything. And I think that story just kind of speaks to what we're trying to do at Fellow, which is essentially leverage the background that we have in semiconductor capital equipment manufacturing and process development, and bring some of that experience into metal additive manufacturing. The systems aren't that dissimilar. They're actually pretty similar when you look at a lot of the components that go into it. And when you want to model the most mature manufacturing solution that exists, semiconductor is a great thing to steal from. And that's what we're really trying to do at Fellow 3D, is leverage all of that experience in manufacturing pedigree into a system that really is a production solution for metal additive manufacturing. Thanks. Any questions?